This video will build on the model introduced in part 1, but it will be a lot less mathematical because it is more about limitations and possible improvements of the model and the historical context that led mathematicians to study this model. The entire model is dependent on this offspring distribution, but obtaining even an estimate of these probabilities is very difficult. A way to do an estimate is like this. Given a number of new coronavirus patients, we need to trace back to who directly spreads the disease to each new patient. In this illustration, the number of branchings involved is 5. The number 5 here can be thought of as sample size for the branching, and we need to make this as large as possible. Taking large enough sample size, we have a more reliable estimate of these probabilities, which are estimated by the proportion of branches having 1, 2, 3 or more offspring. However, this is quite difficult to do, particularly the tracing part. This is made easier with a more widespread implementation of contact tracing, but in the beginning of the pandemic, it is practically impossible to obtain the probabilities that we want. So this is a practical limitation of the model. The second limitation is a bit less obvious and actually more like a possible improvement. If we run this model long enough, then it is entirely possible that the nth generation has more individuals than the world population, which is certainly impossible. The way to work around this is to relax the constraint of the same offspring distribution that we assumed for the BGW process. So for all these offspring distributions, rather than these being all fixed, we can make it a function that changes from generation to generation. Here, the independent variable x can be the total number of infected individuals. These functions might look like this, where it becomes more and more likely that there would be 0 offspring from each branch because coronavirus gradually runs out of people to infect. In turn, the other probabilities will become smaller and smaller. However, since the offspring distribution differs from generation to generation, this is no longer a BGW process, but instead a size-dependent branching process. There can be a lot more different improvements to the model, detailed in this article. It starts off explaining the BGW process, then extends it to the size-dependent branching process we have just discussed, and then generalizing further to a model where similar diseases are in competition, which I genuinely hope isn't useful during this time. This paper finally discusses an even more general model, where it takes into account the factor of age, incubation period, and so on. However, even though each step of generalization gets us closer to reality, the math involved gets much more complicated, or the computing power required will be higher and higher. If you want to read this paper in full, there is a link in the description. The last limitation that I can think of is a bit more pragmatic. The reason why we are interested in the distribution of xn is that we want to see the trend of the spread of coronavirus, and the underlying assumption is that every generation spreads the disease simultaneously. But in reality, it might look something like this, where the generations do not necessarily match up in time. To tackle this, we interpret the generation gap to be a fixed amount of time, say a day. Then xn would truly represent the number of infected individuals on a given day. But that would mean sometimes these 3 dots could represent the same person if the patient hasn't recovered in these 2 days, so we will have to adjust the probabilities in the offspring distribution to account for this. All this is to say that no mathematical models are perfect. They are at most approximations. The perfect mathematical model would be the real world itself. And especially in the coronavirus pandemic, it is all subject to people's responses to the pandemic, including government policies and, more importantly, people's compliance with the government policies. With the limitations set, it is now time to move on to a less negative side of things, which is to see why mathematicians wanted to study this process in the first place. Bien-Aimé was a French statistician, while Galton and Watson were both English mathematicians, and Watson was also a reverend. These mathematicians were concerned with why family names disappear over time. Galton and Watson investigated this problem back in 1873, and for a long time, historians didn't even know Bien-Aimé was related to this in any way, which is why it is still more widely known as just Galton-Watson process. But in fact, Bien-Aimé investigated this problem way earlier than the two. What's more ironic is that Galton and Watson's work was partially wrong, and we will see where they were wrong in a minute. As a very quick side note, Bien-Aimé was also known for this very useful inequality in probability, but it is much more widely known as just Chebyshev's inequality without Bien-Aimé's name. This is not really relevant, I just feel very sad for Bien-Aimé. These people were not the only ones interested in this problem, but as Galton pointed out in the preface of this paper, the conclusion has been hastily drawn that a rise in physical comfort and intellectual capacity is necessarily accompanied by diminution in fertility, using that phrase in its widest sense and reckoning abstinence from marriage as sterility. In other words, other people answer this question by simply saying that people don't reproduce as much anymore. However, Galton and another person, de Candolle, realized that we can explain it the other way. By the ordinary law of chances, a large proportion of families are continually dying out. This means their answer to this question was basically by math. So Galton resorted to using maths to model family reproduction. In the preface of this paper, he wrote that he took considerable pains some years ago to obtain numerical results in respect to this very problem, but the computation became intolerably tedious after a few steps, and he had to abandon it. He then asked this on the Educational Times, hoping that someone could answer. Unfortunately, no one really cared, so he asked his friend Watson to take this problem. Watson used a very similar approach with generating functions that we discussed. The only difference was that he considered the finite case only. His conclusion was wrong though. Watson concluded that all the surnames therefore tend to extinction in an indefinite time, and this result might have been anticipated generally. We know this is not correct because in this second case, the probability of extinction is less than 1, so not all surnames will disappear. This is probably because to illustrate his method of generating function, he used this generating function, which corresponds to the case where it is equally likely to have 0, 1, and 2 offspring. This is precisely this graph over here in the first case, so he might have assumed all cases look like this. What about Bien-Aimé? Well, unfortunately I don't know French, so I wouldn't be able to read or quote anything from his paper. But historians analyzed his paper and found out that Bien-Aimé had not merely discussed what we come to think of as the Galton-Watson problem, but had done so in such a way as to make it plain that he was in possession of the whole criticality theorem, which in this case meant the 2 cases that we discussed, or 3 if you want to count the special case as well. So this is the historical context of the BGW process, but even though it originally had nothing to do with coronavirus, it can be easily applied to model other phenomena unrelated to family names. If you enjoyed this video, give it a like and subscribe with notifications on. See you next time.